Okay, we are in this video going to be looking at the different types of statistical tests one should use depending on what kind of data one has. So there are, as you see, all the green squares or boxes in this this diagram are different types of tests, and when we want to do a statistical test, we can use these different ones depending on what type of data we have. So this is a kind of flow chart that we start from the top here to ask ourselves to kind of arrive at one and use different questions to see what kind of test we should use to kind of move through this flow chart to arrive at one specific test. So we'll start from the beginning here. So depending on the type of data you have, do you have basically continuous data? That is data that is just different numbers, basically. Continuous means that you have numerical data. So the first one, this is basically where it's gonna be a little bit interesting. But the first kind of test we can get to is a chi-square test. Chi-square tests are used to test, for example, the frequencies in an observed experiment compared to what we would expect. For example, in a number of coin tosses we use, did the frequency of heads or tails correspond to what we expected? And it has a few more examples of that too, but I rarely use chi-square tests myself, so maybe I'm not the best at to explaining which one. But usually we end up in some other types of data. We want to perhaps compare some continuous data instead. So the next step here would be then, if we're not going to use a chi-square test, is a type of question we want to ask. So do we want to look at the possibility of a relationship between two continuous variables? So variables that have that both the independent and dependent variables are numerical. So both what we have on our x-axis and on y-axis, are they both numerical? Then we want to do either a regression test or a correlation test. The other option is that we compare the differences between the mean of one group or many groups. Then we get over on this side. But let's continue first with these types of regression tests. So this is the type, if you have data that you put, for example, on some kind of scatter plot, so then this is what we're looking for. Now we have two types of tests we can do here. A regression test and a correlation analysis are both, these two types of correlation analyses are somewhat similar. Is that they're looking for patterns within two variables that are numerical. So they both vary between, very continuously. So usually, I would say that you want to try to use a regression test if you can. In Excel, these can be found easily as regression tests. So the output of that, would be some kind of function or an equation that explains the relationship between the dependent and independent variables, if there is one. So we'll give you both the equation, a linear equation, depending on what kind of data you have, but usually a linear equation. So this y equals kx plus m kind of linear equation, and it also tells you if it is likely or unlikely that we would observe the kind of pattern that we do based on random chance. So the good thing about this is that this equation that we get out, we can use to predict data beyond the range that we have of our independent variable. Whereas we can also look to see if there's a pattern in our data using correlation analyses. And then we have two types of correlation analysis here, either the Pearson's R or the Spearman's Rho. And one is what we call a parametric test, and the other one is a non-parametric test. And what is the difference here? So, a parametric test has these three assumptions that need to be fulfilled, or that we need to be at least somewhat certain that they are fulfilled. So independent samples means that we haven't tested the same individual several times in the two groups that we're looking at. So, and the other one would be that the data is normally distributed, that it follows a normal distribution, and that the variance between the groups are equal. If we are not sure about that, we should use the Spearman's Rho. So, and the Pearson's R instead is the parametric test. Now, why we use this instead of the regression test is that we don't know, for example, which one is the dependent variable and which one is the independent variable. So we could just as easily switch these two with each other. So we don't know which one. It's not specific for us if we want to know if which variable should be in the x-axis and which one should be in the y-axis. So the output of this one is not an equation, but it's instead these R or Rho variables. So the Pearson's R is, for example, the most interesting here. So this one tells us how much of the data basically follows the correlation pattern. R means that, or an R of 1, it can vary between 1 and -1. If it's 1, it would be that the variable on the x and y axis are perfectly correlated with each other. So if you increase the x variable, you have also always an increase in the y variable, for example. Or a -1 would be instead that that there's a negative correlation between them. So if you increase x, y goes down by an equivalent amount. Whereas the Spearman's Rho, we can't really, it doesn't matter, so to say, how much y increases with one step of x. It just means it's important if y increases at all. So those are small differences, but they are important. So the regression test and correlation analyses are similar, but the regression test gives us an equation that is more useful. We can make predictions into the future with this one, whereas the Spearman's, the correlation analysis, we can only talk about our specific data set. Is there a correlation, or is there some kind of pattern within our data set or not? And the Spearman's and the Pearson's R tells us how strong this correlation is. So those are two different ones we can use. The Pearson R is often used as well to tell us how good the correlation is, and we can sometimes add that into a regression test as well. So use both of them to give just the R value for a regression test as well, or usually the R square value to tells us how much of the data actually follows this regression. So it can be supplemented with this. So quite tricky, but we want to try to stay with the regression test if you can, but we can supplement this with a correlation analysis as well. Both of them can give us a p-value that tells us if the likelihood that this pattern would be observed by chance. And low p-values are usually accepted, or means that tells us that it's a significant correlation or significant correlation in this data set. Okay, let's instead assume that we want to compare the differences between groups. So we have a group of data from different or many data points from different groups of data points. We can actually also have just a single group where we're going to compare the mean versus some hypothetical mean. So let's say we know that the mean height of the population is 1/77 6 centimeters, and I have one group of individuals, and I ask myself, is this group of people on average taller than the average for the whole population? Then I do a 1 sample t-test. So the hypothetical mean would be the average for the whole population, but my single sample group, are they different from this hypothetical? So I give the test, then I do a 1 sample t-test, and I give the group, I provide the group's data, and I provide the hypothetical mean, and I compare these to each other and see if my group is likely to be taller than this hypothetical mean. It's quite rare, but it would happen. I've never ever done one of these tests. It's more often that I do, more common that I do these kind of relationship tests or these differences between many groups. So if instead I want to compare 2 test groups, maybe one is the control group and one is a group that I've exposed to some variable. And I want to see if there is a difference between them. So I could do if I have only 2 groups, so control and 1 test group, and I know that I have I've fulfilled the assumptions of the parametric tests. That is that we have independent samples, normally distribution within each group, and equal variance between the groups. I can do a 2 sample t-test. If I don't have that, I would do a Mann-Whitney Mann-Whitney U-test or Wilkinson's rank sum test. 2 sample t-test is you can find in your Excel. You can also actually do 2 sample t-tests assuming independent samples or unequal variances as well. Then basically you get one of these. So 2 sample t-test with dependent samples or equal variances would be something like this, actually. If you have more than 2 groups of data, we move over here instead. So I've had several test groups, and I might have more variables that I'm interested in comparing. Then I will look into some of these tests as well. Instead, I would look, for example, at a one-way ANOVA or a cross-Wallis instead. And that depends on if I have fulfilled these parametric assumptions. So one-way ANOVA is the parametric test, the cross-Wallis is the non-parametric equivalent to it. So that's basically the types of tests that we can do. There are way more than this, and there are many of these kinds of flowcharts to arrive at one of these specific tests. And if you see some problems with this one, you can let me know, and I can see if I can change this up. But what we usually end up doing is making either a regression test, 2 sample t-test, or some ANOVA is most likely what you're gonna come in contact here at Katedralskolan, I would say, in your kinds of experiments. I hope this has given you some help. So we'll talk to each other later. Bye bye.